So, my name is Ilya Medvedev, and I am CTO at ReadyMac. Today, we're diving into performance engineering in dynamic web. And our journey will cover three key areas. First of all, it's the evolution of the web, from simple pages to dynamic applications. We're going to define what a dynamic web is, its meaning and unique challenges. And of course, we're going to talk about achieving great performance with some practical strategies and real-world examples. So, a few months ago, I visited an exhibition at CERN, and I was thrilled to see this: the world's first web server. It's a remarkable piece of history, but does anyone know what it served? Any ideas? No? So, actually, it served this. The first website, created by Tim Berners-Lee at CERN in 1989, almost 35 years ago. It's static, text-based, and absolutely revolutionary for its time. So I spent some time studying the structure of the site, its source code, and it got me thinking, how did we get from this to this? These are examples of modern websites created, and the contrast is stark. To understand how we arrived here, we need to take a journey through the evolution of the web. And let's start with Web 1.0. Web 1.0 was characterized by static and simple pages. Let's take a look at these examples. Apple's 1992 homepage used an image map. Each colored stripe is a clickable area leading to different sections. Amazon's 1995 website showcased a text-heavy, minimalistic design. And the Space Jam website from 1996, this is actually my favorite one, featured a splash page with animated GIFs, a cutting-edge feature for its time. These sites highlights the era's key features. So first of all, it's a static content. Pages that didn't change, like online flyers. We had basic interactivity, image maps, basic hyperlinks, maybe GIFs, that's it. And heavy use of images for layout and navigation. While simpler than today's standards, these early websites introduced important performance considerations. So, first of all, dial-up networks made every kilobyte count. Image-heavy designs may lead to slow load times, and cross-browser compatibility became a big concern. But this was the foundation everything else is built on. And now let's fast forward to Web 2.0 era. Web 2.0 brought significant changes. Look at these examples from Flickr, Blogger, and Twitter. Flickr launched in 2004, revolutionized photo sharing with its clean interface and user-generated content focus. Blogger, by 2006, made web publishing accessible to everyone. And Twitter, appearing in 2007, introduced real-time web interactions. And what about key features? First of all, it's dynamic content. Pages updated without full page refreshes, thanks to Ajax. Anyone could now publish online easily, that's why we have user-generated content here. And real-time interactions, as we've seen in Twitter's feed, for example. But these advancements introduced new performance challenges. JavaScript became crucial power in dynamic interactions. DOM manipulations increased with more interactive UIs. CSS became more complex to handle those sophisticated designs. Image optimizations became critical, especially for photo sharing websites. And perceived performance became as important as actual load times. These changes set the stage for even bigger shifts to come. And as we entered in 2010s, mobile devices changed everything. So let's break down the key shifts. Sites now had to look good on anything from a small phone to a larger desktop monitors. Great for user experience, but it meant more complex CSS and often larger payloads. We started designing for mobile first, then expanding to larger screens. This forced us to focus on core content and core functionality. We had to optimize for taps, swipes, pinches, and so on instead of mouse clicks. This led to new design patterns and new performance considerations. So, for example, buttons are now sized for fingertips instead of mouse pointers. With slower mobile connections, every kilobyte counted, and now we had performance budgets and, of course, adaptive images. We couldn't serve the same image to all devices anymore. These changes forced us to rethink web performance. Now we had to think about different devices, different browsers, different internet connections, and so on. And now, just imagine trying to juggle all of these when you're building a tool that allows users to create a website without ever writing a line of code. Sounds like a big challenge, right? Picture this. You've got all these complex techniques we've just discussed. Responsive design, performance optimizations, touch event handling, and so on. And now you need to package all of that into user-friendly interface that anyone can use to build a website. And this is ReadyMac. At ReadyMac, this is exactly the kind of challenge we face every day. We're not just building websites, we're building a platform that allows designers to create high-performance websites without ever writing a line of code, without ever seeing a line of code. Now let's talk about what we mean by dynamic web in today's context. For us, dynamic web covers all the complexity that users can create, which you then need to optimize and maintain for peak performance. And this includes content variability. Every project is unique. We're talking about pages that adapt their structure and content based on user preferences. The next one is a really significant challenge for us, unpredictable resource usage. We never know if a user will upload one image or several thousand images to their project. Our platform needs to handle this variability efficiently. We have complex interactions. Modern web pages aren't just for reading. They often include some sophisticated animations, parallax effects, different user interactions, and so on. These features increase the complexity of performance management. From smartphones to tablets to desktops, our project needs to work seamlessly across all devices. And the last one, here's the real challenge, consistent performance expectations. Users expect high performance regardless of the type of their project, whether it's a simple landing page or a huge e-commerce project. It needs to load quickly and run smoothly. This is what we mean by dynamic web. And to give you an idea of what we're dealing with, here are some examples. And let's talk about long pages. And when I say long, I mean this. This is a project with over 500,000 pixels in height. Here we have almost 3,000 widgets, and this is only one HTML page. The challenge here is to manage this large volume of data without compromising load times or scrolling experience. Some users create parallax scrolling projects like this. It should perform smoothly across different devices and connection speeds. It's hard to imagine all of these animations, but even harder to manage them, to develop them. Some projects have layouts that transform significantly based on user device, and ensuring these transitions are smooth and don't impact performance is a complex task. All right, I'm going to share some solutions we've developed. Some of the solutions are pretty simple for today's standards, but it doesn't mean we shouldn't use them. So it all starts with the request to our server, and caching here is crucial. We implement multi-level caching strategies. So first of all, we have CDNs, content delivery networks. We use the different CDN providers to cache static assets and some dynamic content at the edge. This significantly reduces latency for users worldwide. We have application-level caching. So for example, we use Redis to cache server-side rendered HTML. And this is very effective for frequently accessed pages. And we cache results of complex calculations. For instance, we cache variable font features to avoid repeated processing. Speaking of real-world examples, for users with a global audience and content-heavy sites, this multi-level caching strategy noticeably reduced load times, especially for users far away from our main servers. Oops. Once the browser gets our HTML, it's parsing time. We've optimized our HTML structure to prioritize critical content. The real magic happens with our script loading approach. So we break our JavaScript into smaller chunks, loading only what's necessary for the current view. And don't forget that HTTP3 is your best friend when dealing with dynamic imports, as it allows multiple scripts to be loaded concurrently without blocking main thread. Of course, we use different links with rails, prefetch or preload, depending on case, for assets crucial for the initial render. In long-scrolling portfolio websites, we initially load only the scripts for the first viewport. And as the user scrolls, we dynamically load scripts for upcoming sections. And this approach significantly reduces the initial JavaScript payload. And this is great. The rendering phase is where things get really interesting. We use partial rendering and lazy hydration approach. So we don't render the entire page at once. Instead, we render what's visible and progressively render the rest as the user scrolls. And the same with lazy hydration. We only hydrate components as they enter the viewport, attaching event listeners and making them interactive on demand. And here is our custom intersection observer hook in action. It's pretty simple. It's just powered by native intersection observer API. Now, let's talk about images. In ReadyMac, we don't have the luxury of knowing what the user will upload. We've seen everything from tiny icons to massive high-res photos. And images are often the heaviest assets. So our strategy includes, first of all, LQIP or low-quality image placeholders. Let me show you this. Users see a low-res preview instantly, which then sharpens into the full image. We create multiple versions of each uploaded image at different sizes, formats, on demand. And of course, we use src set and sizes attributes to serve the most appropriate image for each device and each viewport. Speaking of examples, for portfolios with numerous high-res images, these techniques dramatically reduce load times and improve the user experience with meaningful content appearing much faster. Typography. Typography is crucial in design, but custom fonts can be performance killers. So we use the font face API for faster, lazy font loading. And this allows us to load fonts on demand rather than blocking the main thread. And also our users can use variable fonts to reduce the number of font files needed. And this approach significantly reduced font-related load times, especially for projects using multiple custom fonts. Now let's talk about bringing the page to life with interactivity and animations. We make heavy use of Web Animations API. And Web Animations API are better for us than traditional CSS or JavaScript animations for several reasons. And first of all, it's performance, of course. Web Animations API runs on the compositor thread, avoiding main thread block. With Web Animations API, we have fine-grained controls. So for example, we can modify animation, any keyframes, sequences, and so on, without recreating them. And it's easier to work with multiple animations. For example, we can tie animations together or tie them to scroll or something like that. And for a user wanting a complex parallax effect with numerous animated elements, refactoring to Web Animations API resulted in smoother animations across devices, reduced CPU usage, and even improved battery life on mobile devices. And the final piece of our performance puzzle was rethinking our state management approach. And this journey is interesting because we've tried almost everything that ecosystem has to offer. So we started with backbone models. It was 2014. It was great for its time, but it couldn't handle our growing complexity. Then we explored React contexts, Redux, Mobix, atomic states with Chatai, proxy-based states with Valtios, Zustand, and so on. Still not quite what we need. Some of them are really great, but sometimes there is a lot of unnecessary stuff in them, and sometimes performance became a big concern. Of course, we try to build our custom in-house reactive class based on use sync external store from React. It worked well, but maintenance became a big concern. And finally, we landed on Signals. Why did Signals win? With Signals, we have faster update time for complex operations and near zero performance overhead for multiple values rendering. And this is an absolute must-have for us, as we often operate with an enormous amount of data within a single page. As we've seen, performance engineering in dynamic web is a complex but crucial field. The web has come a long way since Tim Berners-Lee's first website, and with increasing complexity comes increasing responsibility for performance. The future of the web is dynamic, interactive, and complex, but with the right approach to performance engineering, and can also be fast, smooth, and delightful for users. And that's it from my side. Feel free to ask questions, and if you like working on performance, we are hiring. Thank you for your time.